In this video, I'm going to talk about neutron porosity log that is used to estimate the porosity. One of the most interesting applications of this log is to integrate neutron porosity data with density data in order to have a more accurate estimate of the porosity if we don't have any idea about lithology. In addition, if we integrate neutron porosity log with density log, we are able to identify gas saturated zones in the formation. That is another interesting application of this logging tool. Neutron porosity log is based on the attenuation of high energy neutrons in the formation. And that happens when neutrons collide with hydrogen nuclei. Okay, so when we have some porosity in the rock, those pores may be filled by water or oil, and both of these elements have a lot of hydrogens. So as a result of these collisions, high energy neutrons will be attenuated significantly, and from that we can somehow estimate the porosity. From physics, we know that if we have two masses, m1 and m2, and here we assume that m2 is much greater than m1, and if m1 has the initial velocity of m1 and collides with m2, m1 will be bounced back with the velocity of v2 after collision. So in other words, v2, the velocity after collision, will be very almost the same as v1. So what I want to say here is that as a result of this collision, the energy of m1 will not be attenuated significantly. So when this happens in the formation, if a neutron collides with a large nucleus of formation molecule, for example, for sandstone CiO2 or for calcite CaCO3, in that case, because the nucleus has very large mass, the energy of the neutron will not be attenuated significantly. Now assume that M1 and M2 have the same masses. So in that case, as a result of the collision, M1 will stop and the energy will be transferred to M2. So when this happens in the formation, that happens when neutron collides with a proton. And what element has proton? Hydrogen. Okay, so as a result of the collision of neutrons with hydrogens in formation, the energy of neutron will be attenuated. And this is how this logging tool works. Okay, so when we have more hydrogen in the formation, it means that we have higher porosity. In that case, the energy of neutrons will be attenuated significantly. As a result of collisions of neutrons with hydrogen nuclei, we may have three different scenarios. In the first scenario, it is possible that the energy of neutron is attenuated, but not that significantly, and therefore we're going to have moderate energy neutron. So when we talk about moderate energy neutron, it means that the neutron whose energies lies between 0.025 electron volt to 100 kilo electron volt. This range of energy is called epithermal neutron. Another scenario is that neutron will significantly loses its energy, and when I say about very low energy neutron, which means that the energy of neutron even is below 0.025 electron volt. In such a scenario, we're going to have low energy or thermal neutron. And it is possible that, in the third scenario is that the neutron is completely stopped, and in such a case, a gamma ray will be produced. So these are the three scenarios that happen as a result of collisions of neutrons with hydrogen nuclei. So what source we use in order to produce high energy neutron, we may use radium, mm, beryllium, or americium, beryllium to produce high energy neutrons. Different logging tools have been introduced to estimate the porosity from neutrons. One of them is Sidewall's neutron log, or SNP. And this logging tool is based on measuring epithermal neutron. And this logging tool has just only one detector. And from the name, you may notice that it is clamped to the formation. Okay, so for example, if we have a borehole wall here, and if it is our logging tool, it's gonna clamp to the formation by using a bowstring. And here, as I said, you have one detector, and we have one neutron source here. This logging tool has some advantage. The major advantage is that it is less sensitive to lithology. If you remember, I said in order to estimate the porosity from neutron, we should have some idea about lithology. And for this logging tool, because it is based on measuring epithermal neutrons, it is less sensitive to lithology. It means that if we have wrong assumption about lithology, the estimate will not be that, horrible compared to other logging tools that are based on thermal neutrons. It means that, the estimate of the porosity is not accurate, but not horrible. But it has a major disadvantage, and disadvantage is that it has just single detector, and as a result, it is very sensitive to the borehole roughness. So we learned that in the my density lecture, that the borehole wall is not flat. It has a lot of roughness or unevenness. And for example, if we deal with a condition like that in the borehole, it is possible that here, assume that here is borehole is not flat, and as a result, we may have such a scenario that uh, the clamping is not perfect, and here we have short circuit from neutrons to the detector, and as a result, we're going to have wrong estimate of the porosity using this logging tool. In order to address the problem of unevenness of the borehole wall, another logging tool, compensated neutron log, was developed. This logging tool is based on measuring thermal neutrons, and as you see here, it has two detectors, near detector and far detector. And in order to measure the porosity, what we need to do, we should calculate the ratio of number of neutrons detected by near detector over number of neutrons detected by the far detector. And we know that when, for example, neutron is produced here and travels through the formation, it has to go to a longer route in order to get to the far detector, and as a result, it's going to get more attenuated. And generally, we should expect that the far detector will record lower number of neutrons compared to the near detector. So when we have much higher porosity, or when the attenuation is significant, it means that far detector we record much lower number of neutrons compared to the near detector, and as a result, this ratio will be very, very high, and from which we can have some idea about the porosity. So higher ratio of Nn over Nf that we have, it means that it is higher porosity, and this is how we are able to estimate the porosity from our data. Some charts have been developed in order to convert the ratio to the porosity. And as you see here, there are three curves. One curve is for dolomite, limestone, and sandstone. So this is how we should convert Nn over Nf ratio to porosity. We should have some idea about lithology. For example, if the ratio is 2 and the formation is sandstone. What we do here, we draw a line to cut the sandstone curve here, and from here, we're going to draw a vertical line to cut the porosity axis. And for this example, the porosity is 21%. So now let me pose a question. If the formation is limestone and N over NF is 1.5, how much is the porosity? The porosity is 9%. Just let me ask you another insightful question. For a given N over NF ratio, why do different rocks exhibit different values for the porosity? The answer is that although we know that the major contribution for neutron attenuation comes from hydrogen, but it doesn't mean that the rock matrix has zero contribution to neutron attenuation. Indeed, rock matrix also attenuates neutrons, but not that significantly compared to hydrogens. And that's the reason you see that definitely lithology, we have some idea about lithology because rock matrix also has some contribution to neutron attenuation. Now, just let me ask you another insightful question with respect to the chart. Which rock type more absorbs high energy neutrons? So here you see we have dolomite, we have limestone, and we have sandstone. And look at these ratios. Okay, for example, assume that the porosity is 10% and or 20%, and look at the different ratios that you get, then you may have some idea about what lithology or what rock type absorbs neutrons better. So the answer is dolomite. Okay, for example, if you consider the porosity to be 10%, N over NF ratio for sandstone is about 1.3, for limestone is 1.6, but for dolomite is 2.2. That means that dolomite more significantly attenuates neutrons. Now just let me ask you another question. What will the estimate of the neutron porosity be affected if the limestone or sandstone formations have some fraction of dolomite? So assume that we have a sandstone formation with some dolomite or limestone formation with some dolomite. So what will the estimate of the porosity be affected by dolomite? Yeah. So that cause of somehow overestimation of the porosity because dolomite can significantly attenuate neutrons. Here is the summary of what we have learned so far. So in order to have a good estimate of the porosity, definitely we should have some idea about lithology. And we have two logging tools. One of them is SNP, Sidewall Neutron Porosity Log, and another is CNL. CNL is based on measuring thermal neutrons, very, very low energy neutrons. And as a result, it is more sensitive to the lithology compared to CNP that is based on measuring epithermal neutrons or moderate energy neutrons. When we are in the field, we have to translate or convert the values of N over NF ratio to porosity. And in the software, definitely we have to input some lithology. So usually the default lithology is limestone because limestone has some property between dolomite and sandstone. And this is how it works. Okay, so instead of having like n over nf ratios as outputs of our logging tool, we convert them to some values of the porosity by assuming the lithology be limestone. Okay, when we go back to our office, then by looking at other data that we have, for example, core data, the real log cuttings, then we should, consider the correct lithology. Or in other words, we should correct the value of the porosity based on the assumption of limestone matrix to the correct lithology. One chart has been developed by Shale in order to correct the estimates of the porosity by considering the correct lithology. So what you see here over the horizontal axis, you see it is written porosity recorded on limestone matrix, which means the porosity based on the assumption or the default assumption that lithology is limestone. And on the vertical axis, you see it is written true porosity. And how it works, you see 5 curves here. The curve in the middle is for limestone, and you may notice that for limestone is indeed no correction is needed because uh, the default assumption was correct. So assume that if the lithology, correct or real lithology is limestone, and if the default lithology was limestone, so we didn't make any mistake. But if the lithology is different, then definitely we have to apply corrections. So you see here, we have two dash curves here. One is here at the bottom and another at the top. These two dash curves are used to correct the estimates of the porosity for CNL device. And you see two also solid curves. One is here and another is here. And these two solid curves are used to estimate the porosity for SNP or Sidewall Neutron Porosity tool. Now just let me give you an example. So assume that the porosity recorded on limestone matrix is 10%. If the device is CNL, the correct porosity will be 4%. And if the device is SNP, the correct porosity will be 7.5%. So something that is, you may notice here, just let me highlight what I've written here for you. You may notice here that this correction is needed to obtain true porosity for SNP. Okay, so I mean that in order just to correct the value of the porosity, so the wrong porosity was 10, and in order just to correct it, the error was about 2.5 of unit of porosity. But for CNL, the unit of porosity is 6. It's a huge number in order to get to the correct porosity. So that means that more correction is needed if we have wrong assumption about lithology for CNL. And this is something that I mentioned before. CNL is more sensitive to lithology compared to SNP, and the fact that SNP was less sensitive to lithology is one of its advantages. So if the formation is sandstone and the tool is SNP and the limestone assumed porosity is 20%, how much is the true porosity? Yes, the true porosity is 23%. Yes, you may look at it here. And this is something that you see here. One of the most interesting things that we can do in order to have better estimates of porosity is to combine the data from neutron porosity and density log. So if we combine these two log data, although we have wrong assumption about lithology, not only we can obtain a more accurate estimate of the porosity, but also we may get some idea about lithology as well. So what I'm saying that if we have some idea about lithology, if we have correct information about lithology, the porosity that we get from phi n or neutron porosity log should be equal to the porosity that we get from density log. Okay, but if we have wrong assumption about lithology or fluid in the formation, in that case, it is possible that phi n is not equal to phi d. And in such a scenario, if we combine the two data together, not only we can improve our estimate of the porosity, but also we can get some idea about lithology as well. Just let me explain in next slides. Just let's look at this example from real data. And you see here we have zone A, and in zone A, this is the value of the porosity for phi n, and this is the value of the porosity for phi d. So you see that phi d is minus 15%. We know that minus 15% doesn't make sense. The porosity, the minimum value for the porosity is 0, and the maximum value can be 1. And minus 15 porosity doesn't make sense. So why we have ended up this wrong value for the porosity? If you remember from my density log lecture, I said that whenever we have wrong assumption about lithology, we may end up negative value for the porosity. And that's the reason here we see, and this thing is happening here. Now look at zone B. If you look at zone B, something that is interesting here is that phi n is greater than phi d. And here you may ask me the question, why neutron porosity here overestimates the porosity compared to phi d or the density log. And here for this example, there are two explanations. The first reason is that in zone B, the lithology is mostly dolomite, and we know that dolomite more significantly attenuate neutrons. And the second reason is that the formation is also shale. I'm going to talk about it in more detail later today, that shale also significantly contributes to the attenuation of neutrons. Now let's look at zone C. If you look at zone C here, you may notice that phi n, the porosity estimated by the neutron log, is 14%, and phi d is 2%. Again, as I mentioned, whenever we see phi n is not equal to phi d, it means that the lithology is not correct, and we have to assume the correct lithology. But as I mentioned, if we integrate the two data from phi n and phi d, not only we can have a better estimate of the correct porosity, but also we may be able to have some idea about lithology. There is a chart that has been developed by Shale, as you see here, and over the horizontal axis, you see the values of the neutron porosity. And here you see over the vertical axis on the right side, you have the value of density porosity. And on the left side, you have the bulk density. So what it means that doesn't matter if the values of the density have been converted to the porosity or not, you can use this chart. Okay, so if the density is converted to the porosity, just use the right side axis, and if it's not converted, or you have the raw just values of bulk density, just use the left axis here. And here you see three stems. One stem is for sandstone lithology, another is for limestone lithology, and another for dolomite. Now just let's look at this chart, how we use it. Just what we need to do, for example, go here and pick 14 for neutron porosity as we have it here, and 2 for the density porosity, and find the intersection of these two porosities here. And if you if we do that, we see that intersection falls within this area. Indeed, intersection falls with dolomite and limestone. It means that the formation is mostly dolomite, but it is possible that has some percentage of limestone or sandstone as well. And now you may ask me how we estimate the porosity. Just in order to estimate the porosity, just what we need to do, just uh, interpolate between these two stems. So we have uh, limestone stem and dolomite stem. We interpolate by some lines between them, and from these lines we can read the correct porosity. Here the correct porosity is 8%. So as you see, by combining the data from density log and also neutron porosity log, not only we are able to have some idea about the lithology. For example, here we notice that the lithology is dominantly dolomite, but also you are able to estimate the correct porosity. Now just let me ask you a question. Assume that the density is 2.65 and the porosity is 20%. And what is the correct porosity? So the correct porosity is 12%. If we look at the chart here, you see that intersection falls over the dolomite stem, and from which I can conclude that the lithology is dolomite, and the correct porosity is 12%. You may do this example as well. I assume that phi d is 25% and phi n is 20%. Just let's do this together. If we do that, yes, we are going to notice that the correct porosity is 23%, and this is how it works. And for this example, you may notice that the lithology is mostly or is dominantly sandstone. Now, just let me ask you a question. If you see in this example that you already solved, phi d was 25% and phi n was 20%, it means that in this example, phi d was overestimated. And can you explain why? Okay, so there are two reasons. The first reason, because we had wrong assumption about the lithology. So we assume the lithology to be limestone, by the true or actual lithology is sandstone. So if in this equation we put the value of matrix density for uh, for limestone here, because limestone has higher matrix density than sandstone, we're going to end up overestimation of the porosity using density log. Okay, but if just we insert the correct value of the matrix density for sandstone, that is 2.65 in the equation, we're going to end up the porosity to be 22.2%. That is very close to the actual porosity. Another reason is that here we assume the formation to be limestone, but as I said, the actual formation is sandstone, and we know that in sandstone, neutrons are less attenuated compared to limestone, and this is another reason that why here we have underestimation of the porosity from neutron like. So if you remember, I said that we have a chart here that we can use this chart in order to correct the estimates of the porosity. So here, the porosity based on limestone assumption was 20%. And then by considering the lithology, the correct lithology, we're going to end up the porosity to be 22.5%. So as you see, by considering the correct lithology, phi d and phi n becomes equal. But if we don't consider that using this chart, we were able to get some idea, some estimates of the porosity correct to the actual values. Okay, guys. So if you don't have access to the chart, something that you can do simply is that just calculate the average of phi n and phi d to get some estimate close to the actual porosity. And something that you may notice here, this equation just works for the case of 0% gas saturation. If we have some gas in the formation, we may not be able to use this equation. So if you're confident that there is no gas saturation in the formation, you can easily use this equation as well. Okay, so you may refer to this chart if you have it, because it helps you to have some idea about lithology. But if you're in a situation that you don't have this chart, just calculate the average of the two porosities, and again, it's going to give you a very good estimate of the actual porosity. Now, now let me talk about gas saturation. So one of the most interesting applications of combining neutron porosity and also density log is to identify gas saturated zones. If you remember from my density lecture, I said that if we don't assume gas saturation in the formation, we're going to end up overestimation of the density porosity, because in gas saturated zones, usually one of the most interesting applications of one of the most interesting applications of combining neutron porosity and density log data is to identify gas saturated formations. If you remember from my density lecture, I said that if we have no idea about gas saturation in the formation and wrongly assume that the formation is saturated by water or by oil, in that case, we're going to end up overestimation of density porosity. On the other hand, something that is interesting here, neutron porosity in gas saturated zones underestimate the porosity. Okay, so if we are collecting the data and if we look at our data, something that is interesting here, in gas saturated zones, we're going to end up very overestimation of phi d and very underestimation of phi n. And indeed, this is something that we can use in order to identify gas saturated zones. But here, before just going and just talk about how we identify gas saturated zones, just let me explain why in gas saturated zones, phi n will be underestimated. In order to better explain this, just let me ask you a tricky question. So this question is tricky. Assume that we have two different rock types, A and B, and as you see here, the porosity of B is twice of A. Okay, so in other words, in B, in rock type B, as you see here, we have double porosity compared to A. But here is the thing. A is just only saturated by water, 100% saturated by water, but B is 50% saturated by water and 50% saturated by gas. Now assume that we run the neutron porosity over to the two rock types, and just let's see what of these three options we may see. 1, phi b is equal to phi a. The second, phi b is greater than phi n. And the third is phi b is greater than phi a. Okay, guys, so if we run the experiment here, the thing that we're going to notice is that phi a will be greater than phi b. So although the actual porosity of phi b is greater than phi a, but if we run neutron porosity log, surprisingly, we're going to notice that we end up measuring phi a greater than phi b. Here you may ask me why we see this phenomenon here. If you remember, I said that the major contribution to neutron attenuations comes from hydrogen. So you may say that, okay, these two formations, okay, have the equal amount of water. So water has a lot of hydrogens, but this formation has gas. B has gas, and gas is composed of hydrogen. But here is the problem. There is a huge space between two gas molecules, and as a result, although gas molecules are composed of hydrogens, they cannot that effectively attenuate neutrons. Okay, so that's the thing. Here we have matrix, and the other we have gas. So just let me pose you this question. Assume that here we have just pure matrix, and here we have pure gas. So which one attenuate neutron better? And as I said, because there is a huge space between two gas molecules or between gas molecules, and for that problem, gas less effectively can attenuate neutrons compared to matrix. So here, because we have more matrix here compared to B, and matrix attenuates neutron better than gas, this is the reason why we're going to see this observation. We're going to see that phi d will be greater than phi b, phi a will be greater than phi b. And indeed, this phenomenon is called excavation effect. So excavation effect means that gas cannot attenuate neutron significantly, and even matrix itself is able to attenuate neutrons much better than gas. And so whenever we have some gas saturation in the formation, we're going to end up underestimation of the porosity using neutron log. So in other words, if we deal with the gas saturation formation, we should see that phi d will be much greater than phi n, and this is how we are able to identify gas saturated zones in the formation. Now just let's look at this data. As you see, we have the red curve corresponds to density porosity, and the dash curve here corresponds to neutron porosity. And here, just look at the scale here. The right side is minus 15, and the left side is 45. And then by comparing the data first, by looking at, for example, gamma ray data, identify permeable zones. Within the permeable zones, identify gas saturation, saturated zone. Okay, guys, so if you look at the data here, you see that, for example, this zone is a permeable zone. This zone also is a permeable zone because we see so this zone is permeable. Also, this zone is permeable. And also, I can say that, for example, this zone is permeable. And how I am able to identify these permeable zones based on the reading of gamma ray. So the gamma ray is a little bit low, so I can consider these zones to be permeable. Within this permeable zone, if you look at it here, you see that, for example, phi n here is about, for example, in this zone is about like 5%, but phi d is about 30. So I can consider this zone to be gas saturated zone. Now just let's go back and look at the chart that I've already talked about. If the intersection of neutron porosity and density porosity falls within this area that I've highlighted by the blue color, it means that that zone should be gas saturated zone. For example, assume that the neutron porosity is 0% and the density porosity is 40%. And as you see here, the intersection falls here, and this is in the blue area, and I can say that that zone is a gas saturated zone. So this is one way in order to identify gas saturated zones. Now here you may ask me a question, how we are able to estimate the density, okay, when we have gas saturation. In such a case, definitely we have to have some idea about lithology as well, okay, in order to estimate the correct porosity. And how we are able to do that, again, we find the intersection, and then what we do here, we draw a line parallel to this arrow, as you see here, to cut the correct lithology, and then from which we read the correct porosity. Okay, so for example, here you see phi d is equal to 22, phi n is 4, and I find the intersection here, and from the intersection, I draw a line parallel to this arrow to cut the dolomite stem. And on the dolomite stem, I notice that the correct porosity is 14%. Now just assume that phi d is equal to 24.5 and phi n is 6, and the formation is limestone. So what is the correct porosity in this example? So the correct porosity is 16.5, and this is how you may estimate it. Again, if you don't have access to this chart, you may use this equation for the case of gas saturation. So what you need to do, calculate phi d square plus phi n square, and calculate their average, and then calculate their square root. Now assume that phi d is 40% and phi n is 33. What is the correct porosity? So if you look at this the chart, you may notice that the correct porosity is 38%. So this is an example that the formation is not saturated by gas, but you see that phi d is greater than phi n. So here you may ask me why, we end up this situation. And the reason, because again, wrong assumption about lithology here. The lithology, the actual lithology is sandstone, but we wrongly assume to be limestone. And for sandstone, so as you see here in this example, phi d is greater than phi n, but it is not saturated by gas. And the reason, because of sandstone. So in sandstone formations, again, we're going to end up with overestimation of density porosity and underestimation of neutron porosity. Something that you may notice here in this example, phi d was greater than phi n, but the formation wasn't gas saturated. The formation was sandstone. This is something that happens again in sandstone formations, similar to gas saturated formation with phi d is greater than phi n. But here is something to avoid false gas indication, is that if the phi d is much greater than phi n, then we can say that that formation should be gas saturated. So in other words, if the difference between phi n and phi d and phi n is greater than 10 porosity unit or 10%, in that case, you will say that that formation is saturated by gas. If the difference is below 10, likely that formation is sandstone, and you shouldn't say that, okay, this is a gas saturated formation. So this is something that you should consider in order to correctly interpret your density and also neutron porosity log data. Now just let me ask you another question. And do we have underestimation of neutron porosity in gas saturated zone of a shale formation? The answer is no, because the presence of shale somehow mitigate the excavation effect. Indeed, clay minerals can absorb a huge volume of water, and that water is bound to the clay. And that's the thing, if we have some shale in the formation, shale is composed of clay, and as a result, that clay will somehow attenuate a lot of neutrons in the formation, and this is how it's going to mitigate the excavation effect. Here we have a problem, okay? And the problem is that if the formation is shaly, we don't see excavation effect. And if we don't see excavation effect, we are not able to identify gas saturated zones by looking at density and neutron porosity data. So how we are able to identify gas saturated zones for shale formations, for example, shale sandstone or shale limestone? Indeed, there is a solution for that, and the solution is to use epithermal neutrons. So if you remember before, I said that CNL, or compensated neutron log, is based on counting thermal neutrons. And thermal neutrons are kind of very low energy neutrons that can be easily absorbed by the shale formation. If we use epithermal neutrons in order to measure the porosity, because epithermal neutrons are a little bit kind of moderate energy and they have more energy compared to the thermal neutrons, they are less affected by clay in the formation, and this is how we're able to see the excavation effect. So the solution to this problem is to use epithermal neutrons instead of thermal neutrons to see the excavation effect in shale formation in gas saturated zones. So in order to address the problem of gas saturation, a more advanced version of neutron porosity log has been developed, and that is dual porosity compensated neutron log. As you see in this logging tool, the neutron source is in the middle, and we have two thermal detectors at the top and two epithermal detectors at the bottom. So this logging tool not only measures the thermal neutrons, but also epithermal neutrons. And because, as I mentioned, epithermal neutrons are less affected by shale, so they can help us to see excavation effect in the shale formations from which we are able to identify gas saturated zones. So here is an example. So what you see here, and this is the density log data. and here gamma ray data. And as you see, the reading of the gamma ray is quite high. It means that this formation is shale. And in the middle, what you see here is phi d versus phi n that has been obtained by thermal neutrons. As you see, although here phi d is somehow overestimated, excavation effect is not seen on phi n. You see the values of phi d and phi n are almost equal. And this is because of the presence of shale in the formation. And we are not able to say anything about gas saturation here. But when we use epithermal neutron here, you see that epithermal neutron again underestimates the porosity, the neutron porosity compared to phi d. And here we are able to see the excavation effect here, from which we are able to say that this zone should be saturated by gas. I hope that you have enjoyed the lecture. So in this lecture, you learn how to, first of all, look at neutron porosity log data, then how to integrate neutron porosity log data with density data in order to have a better estimate of the porosity and also to have some idea about lithology. And also you learn that how to identify gas saturated zones by looking at density and neutron porosity log data together. And also you learn how to identify gas saturated zones in shale formations. I hope that you have enjoyed the lecture. Thank you a lot for your attention.
So